So I got a lot of messages and comments from people after the video about Cantor's diagonal proof suggesting the following. If you can take a supposed infinite list of all rational numbers and prove it can't ever contain all rational numbers because you can take one key digit from each number and make a new real number that's different in every key digit and is therefore not on the list, no matter what the list is, why can't you reverse this process? Try to make a list of all whole numbers and prove that there's more whole numbers than whole numbers by going on the other diagonal. A reverse Cantor. I kind of like this line of thinking. On the one hand, it's a mathematical way of thinking. If a proof seems to prove one thing is weird, you should probably test it on other things to see if it works, if it proves everything is weird. And if everything ends up weird, you might have a flaw in your premise or your thinking, or maybe everything actually is weird. On the other hand, I don't like this line of thinking because it reminds me of the slippery slope fallacy. That's the one where you're like, well, if this argument works for this case, then why wouldn't it work for this other, more general case, and who knows where it will stop? So we'd better not allow this in the first place. And that's not actually a logical or mathematical argument if you don't prove it actually does apply to the more general case. So can you do the reverse Cantor? Does this argument actually apply? If you take one digit from each number on your infinite list of all whole numbers and change them all, shouldn't you get something that can't be on this list, thus proving the list is incomplete? Well, you do get something not on the list, so that part of the reasoning is correct. Let's try it out. For every list item, we have a decimal place with a number in it. There's as many list items as decimal places, and there's an infinite number of each. That means that this number we're constructing will have infinite digits going out to the left, all of which conflict with the corresponding list number's nth decimal place. Now, the list of all whole numbers is infinite and includes arbitrarily large numbers approaching infinity, but no real number, no counting number, no whole number is actually infinite. They all stop somewhere. They all end up with infinite zeros at some point. But this number we're constructing doesn't stop. It has to have infinite digits going out to the left in order to conflict with every number in every decimal place. No infinite zeros, so no, it's not on the list, but it's also not a badly named so-called real number. Real numbers can have infinite digits going out to the right. Any combination of digits going out to the right infinitely. No last digit. 0.9 repeating actually exactly equals 1, and pi never ends or repeats, and any random roll of infinite dice is a number different from the same number with one random digit randomly changed. That's how many digits there are, etc. Which is why the proof does work for reals. It's all in the decimals, the in-between. But real numbers can't have infinite digits going out to the left. The counting numbers approach infinity, but they don't get there. And they certainly don't go past it, so the reverse Cantor is not a problem. But it is interesting to think about what it might mean to extend the real numbers to include ones that do have infinite digits going to the left. I mentioned p-adic numbers in a video about kinds of infinity, and p-adics have infinite digits going out to the left, but they don't work the same way as reals, so this doesn't actually represent an infinite number. But what if you could represent infinite numbers like this? What would that mean? You'd run into some difficult questions. How do you define them? Is this number bigger or smaller than this number? You can't compare the leftmost digit because there is no leftmost digit. Are they all equal? Simply infinity? How do you add them? If you do it the normal way, isn't it weird that adding ... 55555.0 to ... 55555.0 is ... 00000? There's no leftmost digit for the 1 to get carried to, so it's just gone, which is the same as you'd get if you subtracted them. I think it probably all devolves from there, because if ... 55555.0 equals negative ... 55555.0, then just add ... 55555.0 to both sides, and you get 5 equals negative 5, and from there you break all of mathematics for all numbers. So you definitely can't do arithmetic the obvious way, if at all. Or maybe ... 00000 is an infinitely large number that's different from just plain 0, which is a nice concept if you can find a way to make it work. I don't know. There's alternate number systems where negative 0 is different from positive 0, so maybe there's a way. I don't know. You can figure it out. I'm going to bed.